Class 10 Real Numbers Part 2. In today's session, we discuss Euclid's division algorithm. Before that one, we try to understand Euclid's division lemma. To understand the concept of Euclid's division lemma, we consider some examples and then generalize the concepts to understand Euclid's division lemma. Let us consider the case when divisor is true. That is, if we divide any number by 2, what is the remainder? Here, we have divided 5 by 2, we got remainder 1. And we can write 5 equal to 2 into 2, that is dividend equal to divisor into quotient plus remainder. 5 equal to 2 into 2 plus 1. Similarly, we consider 18 and it is divided by 2. We got remainder 0. So 18 can be written as 2 multiplied by 9 plus remainder 0. We consider another example, 57. 57 is divided by 2 and we got remainder 1. And 57 can be written as 57 equal to 2 multiplied by 28 plus remainder 1. So what is the remainder when 76 is divided by 2? The remainder is 0. So our observations, what is our observation? Our observation is that when 2 is the divisor, then we got 0 or 1 as the remainder. This can be written as 0 less than or equal to or less than 2. 0 or 1 are the remainders, either 0 or 1 when divisor is true. And we know the property divisor dividend equal to divisor multiplied by quotient plus remainder. Dividend equal to divisor multiplied by quotient plus remainder, this property. Now we consider the case when a number is divided by 2, 3, then what will be the remainder? Here I considered 27. We have divided 27 by 3, we got remainder 0. 28 is divided by 3 and we got remainder 1. 29 is divided by 3, we got remainder 2. And here in this case 27 is written as 3 multiplied by 9 plus 0. 28 is written as 3 multiplied by 9 plus 1. 29 is written as 3 multiplied by 9 plus 2. That is, the remainder value is less than divisor and greater than or equal to 0. So when 3 is the divisor, we got remainders 0, 1 or 2. Remainders 0, 1 or 2. This is written as 0 less than or equal to or less than 3. We have written here 0 less than or equal to remainder less than a divisor. We know the formula dividend equal to divisor multiplied by quotient plus remainder. In this case also, these concepts are verified. Now we consider the case when divisor is 4. When divisor is 4, I consider 104 divided by 4, the remainder is 0. 105 divided by 4, remainder is 1. 106 divided by 4, remainder is 2. 107 is divided by 4 and remainder is 3. So, and all these are dividend equal to divisor multiplied by quotient plus remainder. We can express like this. So, when divisor is 4, we got the remainders 0, 1, 2 or 3. When divisor is 4, reminders may be 0, 1, 2 or 3. Now, we have written again the property 0 less than or equal to remainder less than divisor. Dividend equal to divisor multiplied by quotient plus remainder. Now we consider the case when divisor is 5. When divisor is 5, we may get the remainder equal to 0, remainder equal to 1, remainder equal to 2, remainder equal to 3 and remainder equal to 4. So we considered different numbers 365, 366, 367, 368, 369. When these numbers are divided by 5, we got reminders 0, 1, 2, 3, 4. If any number is divided by 5, then we get the remainder 0 or 1 or 2 or 3 or 4 only. And we can express we can conclude that when divisor is 5, the remainders may be 0, 1, 2, 3 or 4. We have observed several examples in this case. Now, we noted down the formula dividend equal to divisor multiplied by quotient plus remainder and 0 less than or equal to remainder less than divisor. Similarly, if n is the divisor, then and n is the natural number. If n is the divisor and n is the natural number, then the remainders may be 0, 1, 2, 3 or and so on up to n minus 1. We may get any one of these numbers as the remainders. And it is written as 0 less than or equal to remainder less than n. Now, generalizing this concept, if A is the dividend, B is the divisor, C is quotient and D is remainder, where A, B are natural numbers and Q, R are whole numbers. Q, R are whole numbers, A and B are natural numbers. A and B are natural numbers, then we can write dividend equal to divisor multiplied by quotient plus remainder. Here A is dividend, B is divisor, Q is quotient, R is remainder. And we have observed that 0 less than or equal to remainder less than divisor. 0, R is remainder and B is divisor. So we get the remainders 0, 1, 2, 3 and so on up to B minus 1. Here we must remember that Q and R are whole numbers. Q and R are whole numbers. So this is the generalized concept. Now let us consider the actual Euclid's division lemma. According to Euclid's division lemma, given positive integers, A and B are positive integers, there exists a unique pair of integers Q and R. This is unique pair. Unique pair of integers Q and R such that A equal to BQ plus R. A equal to BQ plus R, that is dividend equal to divisor multiplied by quotient plus remainder, and 0 less than or equal to R less than B. We have seen several examples. This is Euclid's division lemma. Now, again, students must understand this concept. A equal to BQ plus R, where A is the dividend, A is dividend, B is divisor, Q is quotient, R is remainder. And the remainder value is from 0 to B minus 1. That is where B is the divisor. 0, 1, 2, 3 and so on, B minus 1. So this unique pair, what is unique pair? Q and R are unique pair. For any given positive integers A and B, there exists a unique pair of integers Q and R satisfying the condition A equal to BQ plus R, where 0 less than or equal to R less than B. Now we consider some important points about Euclid's division lemma. Euclid's division lemma is, it was first recorded in Euclid's Elements. In Euclid's Elements, book 7. We already studied that Euclid has written the Elements, which consist of 13 books. Euclid's division algorithm is based on this Euclid's division lemma. This is second point. And third one is Euclid's division algorithm is used to find out the highest common factor of any two given numbers. Euclid's division algorithm is used to find highest common factor of two given numbers. HCF of two positive integers A and B. What is the highest common factor? The highest common factor of two positive integers is defined as the greatest positive integer D such that D divides both A and B. Now we can understand the concept of highest common factor by considering some example. Consider two numbers 60 and 100. Now we note down the common factors for 60 and 100, 2, 4, 10 and 20. 2 divides both 60 and 100. 4 divides both for 60 and 100. 10 divides both 60 and 100. 20 divides both 60 and 100. But what is the highest common factor which divides both 60 and 100? 20 is the highest common factor which divides both 60 and 100. Therefore, HCF is 20 for the numbers 60 and 100. Now we consider some find whole numbers Q and R for the following pair of positive integers A and B satisfying A equal to BQ plus R. Given A equal to 13, B equal to 3. That means 3 is the divisor, 13 is the dividend. So we have divided 13 by 3, we got remainder 1. 3 fourths 12. So 13 can be written as the product of 3 and 4 plus 1. Dividend equal to divisor multiplied by quotient plus remainder. Therefore, Q equal to 4 and R equal to 1. We consider the problem A equal to 8, B equal to 80. That is, dividend is 8, divisor is 80. Here in this case, the divisor is smaller number than the dividend is a smaller number than the divisor. So, 80 divided by 8, quotient is 0 and the remainder is 8. Therefore, 8 can be written as 80 multiplied by 0 plus 8. Hence, quotient is 0 and the remainder is 8. Why? Because the dividend A is less than divisor B. 8 is less than 80 and 8 is the dividend, 80 is the divisor. We should not change the order of this one. It is given in the textbook that A is the dividend and B is the divisor. Now we consider another problem. A equal to 125, B equal to 5. That is, the divisor is 5 and the dividend equal to 125. When 125 is divided by 5, we get remainder 0 and quotient 25. Now the dividend 125 equal to divisor 5 multiplied by quotient plus remainder 0. So this is in the form of A equal to BQ plus R, where A is dividend, B is divisor, Q is quotient, R is remainder. Therefore, Q equal to 25, quotient is 25 and remainder is 0. Now we consider another example. A equal to 132, B equal to 11. So, when 132 is divided by 11, we get quotient 12, remainder 0. So 132 can be written as the product of 11 multiplied by 12 plus 0. That is, dividend 132 equal to divisor 11 multiplied by quotient 12 plus remainder 0. This is in the form of A equal to BQ plus R. Hence, Q equal to 12 and R equal to 0. Now, we consider the problems using Euclid's division algorithm to find the highest common factor of any two given numbers. Use Euclid's division algorithm to find HCF of 50 and 7015. Now we note down the Euclid's division lemma. Given two positive integers a and b, there exists a unique pair of integers q and r such that a equal to bq plus r and 0 less than or equal to r less than b. First, we have to note down the statement of Euclid's division lemma before solving the problem to find out the highest common factor. Now, So 7015 is divided by 50 and we got quotient 140 and remainder 15. Therefore, dividend is written as the product of divisor 50, quotient multiplied by quotient 140 plus remainder 15. Dividend equal to divisor multiplied by quotient plus remainder. So this is the first one. In the second one, with this remainder, the divisor must be divided. So now 15 becomes the divisor, 50 becomes the dividend. When it is divided, 15 divides 50, we get remainder 5 and quotient 3. Therefore, we can write 50 equal to 15 multiplied by 3 plus 15, 5 plus 5. 50 equal to 15 multiplied by 3 plus 5. That is the dividend equal to divisor multiplied by quotient plus remainder 5. Now, we have to divide 15 by the remainder. That is the divisor 15 should be divided by the remainder 5. This process continues until we get to the remainder 0. So now, $15 is divided by 5, we got remainder 0. Therefore, this is the last step. 15 can be written as the product of 5 multiplied by 3 plus 0. That is the dividend equal to divisor multiplied by quotient plus remainder. So now we got the Euclid's division algorithm, the first step, second step and third step. So when remainder is 0, then the divisor becomes a HCF. So therefore, HCF of 50 and 7015 is 5. This is the process of finding HCF of two positive integers using Euclid's division algorithm. Now we find HCF of two numbers 428 and 82,152 using the Euclid's division algorithm. We note down Euclid's division lemma. Given positive integers a and b, there exists a unique pair of integers q and r satisfying a equal to bq plus r, where 0 less than or equal to r less than b. So, first we have to write the statement of Euclid's division lemma. Then, the larger number is divided by the smaller number. 428 is the divisor, smaller number is the divisor, larger number is the dividend, 82,152. When it is divided, we get quotient 192 and remainder 404. Therefore, the dividend can be written as the product of divisor and quotient. Divisor and quotient. 428 is the divisor, 191 is the quotient, plus remainder. Dividend equal to product of divisor and quotient plus remainder. So we have noted down. Now we have to divide the divisor by remainder. So 404 becomes the divisor, 428 becomes the dividend. So when 428 is divided by 404, we get quotient 1 and remainder 24. So dividend 428 can be written as the product of divisor 404 and quotient 1 plus remainder 24. 428 equal to dividend equal to divisor 404 multiplied by quotient 1 plus remainder 24. Now we have to divide the divisor by remainder. Now 24 becomes the divisor, 404 becomes the dividend. When it is 404 is divided by 24, we get quotient 16 and remainder 20. So dividend 404 equal to divisor 24 multiplied by quotient 6. Quotient 16 plus remainder 20. Now remainder divides the divisor. Remainder 20 divides the divisor 24. 20 becomes the divisor, 24 becomes the dividend. When 24 is divided by 20, we get remainder 4 and quotient 1. Quotient 1. So 24 dividend 24 can be written as the product of dividend and quotient. 20 multiplied by 1. 20 is the divisor, 1 is the quotient, plus remainder 4. Plus remainder 4. Now we have to divide the divisor 20 by remainder 4. By remainder 4. So 4 becomes the remainder, divisor, 20 becomes the dividend. When it is divided by 20 is divided by 4, we get remainder 0. Therefore, this is the last step. That means in this case, this 4 becomes the HCF of the two numbers. 4 becomes the HCF. Divisor 4 becomes the HCF of the given two numbers. So 20 can be written as Dividend 20 can be written as divisor multiplied by quotient plus a remainder. Now we note down all the algorithms. We note down all the algorithms, Euclid's algorithms, and finally we write HCF of 428 and 82,152 is the divisor 4. That means in this the last step we got 0 as the remainder. Therefore, the divisor 4 becomes the HCF. Now we consider another example. Another problem. Use Euclid's division algorithm to find HCF of 2326 and 102546. Two numbers are given. We have to find HCF using Euclid's division algorithm. Now we note down Euclid's division lemma. Given positive integers a and b, there exists a unique pair of integers q and r satisfying a equal to bq plus r and 0 less than or equal to r less than b. We must note down Euclid's division lemma first. Then we divide the larger number by the smaller number. Here the divisor is the smaller number, dividend is the larger number. Now we got quotient 44 and remainder 202. So the dividend equal to divisor multiplied by quotient plus remainder. Now we must divide the divisor by the remainder. Divisor must be divided by the remainder in the next step. So 202 becomes the remainder in the earlier step becomes the divisor. The divisor in the earlier step becomes the dividend here. When this is divided, 2326 is divided by 202, we got quotient 11 and remainder 104. Therefore, dividend 2326 equal to divisor multiplied by quotient. Divisor is 202, quotient is 11. Plus remainder 104. Now, in the next step, we divide the divisor by the remainder. Divisor must be divided by the remainder. That is, 202 should be divided by 104. So 104 is the divisor, 202 is the divisor. So quotient is 1 and remainder is 98. Therefore, dividend 202 equal to divisor 104 multiplied by quotient 1 plus remainder 98. Now, in the next step, we divide the divisor by the remainder. That is 98 divides 104. 104 is divided by 98. In this case, we get quotient 1 and remainder 6. Therefore, the dividend 104 is expressed as the product of divisor multiplied by quotient plus remainder 6. Now, we have to divide the divisor by the remainder in the next step. In the next step, we have to divide the remainder. We have to divide the divisor 98 by the remainder 6. So, when 98 is divided by 6, we get quotient 16 and remainder 2. This process continues until we get the remainder equal to 0. So, dividend 98 equal to divisor 6 multiplied by quotient 16 plus remainder 2. Now, in the next step, we have to divide the divisor by the remainder. The divisor must be divided by the remainder. That is, 6 becomes the dividend, 2 becomes the divisor. So, when it is divided, 6 is divided by 2, we get quotient 3 and remainder 0. Therefore, this divisor becomes the HCF of the given two numbers. 6 equal to 2 multiplied by 3 plus 0. So, in the last step, we got remainder 0. Now, we note down the division algorithm for in the obtained in the previous cases. So, when remainder is equal to 0, the divisor will be the HCF. The divisor will be the HCF of the two given numbers. Therefore, HCF of the two given numbers is equal to 2. This is how we find HCF of the two given numbers using Euclid's division algorithm. Find the HCF of two numbers 1555 and 85505 using Euclid's division algorithm. Now, we note down Euclid's division lemma. Euclid's division lemma, given positive integers a and b, there exists a unique pair of integers q and r satisfying a equal to bq plus r and 0 less than or equal to r less than b. Now, in the first step, we divide the larger number by the smaller number. Smaller number is 1555, larger number is 85505. When the larger number is divided by the smaller number, we got quotient 54 and remainder 1535. Therefore, dividend equal to divisor multiplied by quotient plus remainder So this is dividend, this is divisor, this is quotient, this is remainder. Now, in the next step, we have to divide the divisor by the remainder. In the next step, we have to divide the divisor by the remainder. So, this becomes the divisor, 1535 becomes divisor, and this becomes the dividend, 1555 becomes the dividend. When it is divided by 1535, we got quotient 1 and remainder 20. Now, Dividend equal to divisor multiplied by quotient plus remainder. Dividend equal to divisor multiplied by quotient plus remainder. Now, in the next step, we have to divide this divisor by the remainder. This process should be continued until we get the remainder equals to 0. So, 20 becomes divisor, 1535 becomes dividend. When 1535 is divided by 20, we got 76 as quotient and remainder 15. So, dividend 1535 equal to divisor 20 multiplied by quotient 76 plus remainder 15. That is dividend equal to divisor multiplied by quotient plus remainder 15. Now, in the next step, we have to divide this divisor by the remainder 15. That is 20 should be divided by, divisor 20 should be divided by the remainder 15 in the next step. So, when 20 is divided by 15, we get quotient 1 and remainder 5. Therefore, dividend 20 equal to divisor 15 multiplied by quotient 1 plus remainder 5. Plus remainder 5. Now, in the next step, we have to divide the divisor by this remainder. So, 5 becomes the divisor, 15 becomes the dividend. When 15 is divided by 5, we get 3 as quotient and remainder 0. 0 is the remainder. So, we should stop the procedure here. So, 15 equal to dividend 15 equal to divisor 5 multiplied by quotient 3 plus remainder 0. In this, the last step, the divisor becomes the HCF of the two given numbers. The divisor 5 becomes the HCF of the two given numbers since we got 0 as the remainder. Therefore, we note down the Euclid division algorithm which were obtained in the previous steps. Now, in the last step, this divisor, when we got a remainder equal to 0, the divisor becomes the HCF of the two given numbers. Now, students are given some problems as exercises. They should find the HCF of the following positive integers using Euclid's division algorithm.